Let's take a look now at example 4. I want to find a series that sums to ultimately be equal to pi over 6. Okay, so this is kind of a weird task that we've never really been forced to deal with previously. Again, I'm going to try to go ahead and focus on the things that I know about series that we've already looked at. So scrolling back to a previous page, I know that I have all of these series. And I'm curious if any of these series might possibly be able to come out equal to a pi over 6. Well, if I look at all of these, it's possible that maybe I could make the inverse tangent function spit out a pi over 6, since inverse trig functions always return angles. So let's go ahead and take a look here. I want to find a series that sums to be pi over 6. So I might say something like, we know that the inverse tangent function, specifically the inverse tangent of 1 over the square root of 3, is going to come out equal to pi over 6. And you may recall that just from some basic trig facts that you know. But interestingly is that this value of 1 over root 3 is then kind of like a value for x that I would like to be able to go ahead and plug in to my inverse tangent function and its associated power series. Of course, I would like to plug in 1 over root 3, but I can't just plug in any number I want and guarantee that both sides match. I would have to look at the interval of convergence and ask the question, is 1 over root 3 a number inside of the interval -1 to 1? Well, clearly that value is, and so I do know that I could simply just replace x with a 1 over a root 3. So I could go ahead and write something like the following. I could say that since 1 over square root of 3 is in -1 to 1, we know that the series of -1 to the n times a 1 over root 3 to the 2n plus 1 over a 2m plus 1 has to be equal to the inverse tangent of 1 over root 3. Notice that's the exact series and inverse tangent function that we had up in the box above. But we know that this is equal to pi over 6. And so I have easily found a series that adds up to be pi over 6. Now, in the next part, you'll see I ask, why would this problem maybe need to be solved differently if I wanted a series that summed up to be pi over 3? Well, I could start kind of the same way in saying that pi over 3 is I could imagine as an angle measure that the inverse tangent could spit out. But if you try to think here about what value can you plug into the inverse tangent to make it spit out pi over 3? Do you know what value that would be? Well, it's actually going to be the value square root 3. But I might notice something. But square root 3 is not in the interval from -1 to +1. And so I would not be able to use this series representation for the inverse tangent to help me address the problem. So I can't use that, but it doesn't mean that the question's impossible to answer. I might be able to go back to the series that I had and try to think about another way that I could maybe get this to work. And specifically, a type of series that's usually pretty easy to work with is a series like a geometric series, because I know that if I can get a over 1 minus r to turn into a pi over 3, that I'll have found a geometric series that may ultimately converge to pi over 3. The only restriction that I need to have is that, again, r, when absolute valued, needs to be less than 1. So I propose maybe trying to do the following. I'm going to suggest that maybe we go ahead and set up the following values. I want to get pi over 3 using this a over 1 minus r notation. And for the sake of simplicity, let's say that we're going to make r equal to the value of 1/2. That way its absolute value is automatically less than 1. And it's going to make it really easy because down here we're going to get a divide by 2, or sorry, a divide by a 1/2, which will turn into a multiplication by 2. So could you think, if I know that in the next step I'm really just going to have a 1/2 down here, what value would I want up top so all of this can be equal to pi over 3? Well, you might be able to see that this value should be something like pi over 6. Because when I take pi over 6 and I divide by a half or multiply by 2, I get to pi over 3. So this right here, it looks like the sum of a geometric series. And again, I can see that my a is pi over 6 and my r is a 1/2. So I can easily write this geometric series as pi over 6 times a half to the n. And I have a series that actually works with this. Now, of course, not every problem is going to require that I use a specific series or that I use a specific technique. And so I have to kind of be ready to tackle any question in a variety of different ways. And so practice is going to be our number one resource. Consider the next question that we kind of have near the bottom here. Can I find a series now that ultimately sums to be a half times the inverse tangent of a half? Well, there are many different ways that I could possibly deal with this, but I might immediately recognize that, hey, since there's an inverse tangent, maybe I can use the relationship I established up here again, as opposed to going to something like an awkward geometric route and trying to force something like this to occur. Well, let's see what happens. So I can start to say what we know is that this series, -1 to the n, x to the 2m plus 1 over 2m plus 1. We know that this is equal to the inverse tangent of x for all x in the interval -1 to 1. So if this is a building block that we can start with, we can think about how we might want to manipulate to get over to here. Well, this actually becomes pretty simple. We could probably say that it looks like since I want inverse tangent of a half, I could just replace x with a 1/2, and I would know these sides are still equal because 1/2 is in the interval of convergence. So I'll say, since x equaling 1/2 is in the interval of convergence, then we can say that the series with a 1/2 plugged in for x is going to be equal to the inverse tangent function with a 1/2 plugged in for x. Okay, if that's true, then how can I get this to say that this is equal to 1/2 inverse tangent of a half? Well, that actually isn't too hard because I could probably just imagine multiplying both sides of this expression or this equation now by a 1/2. And of course, if I was to do that, I could take that 1/2 and really just multiply it to the inside, since again it's a constant. If I was to do that, notice that I would really be able to just add one extra half kind of onto the stack of 1/2s that I have in the numerator. And so I can end up with the following. So hopefully this shows you that there's a variety of different ways that we can begin to kind of tackle these different sorts of questions that come up. The only technique that we haven't yet talked about from the list that we saw a ways back is this fourth technique of substituting in polynomials, but we will cover that in the next video.